Hello and welcome. Today we're going to take a look at how you can model your structural designs with IC3D Steel and then immediately take them into SOLIDWORKS Simulation to validate them from a structural perspective. Here I have a simple shed design modeled entirely using the capabilities of IC3D Steel. I have my structural members, I have connections such as cleats, bolted eave, splices, and end plates, as well as some base plates. So all of the necessary trimming holes have been drilled and cut, so my model is ready from a design point of view. But before I start cutting any steel, I would like to verify its structural integrity. And because IC3D Steel produces native SOLIDWORKS models, it's completely integrated into the SOLIDWORKS environment, we can very quickly switch to simulation and take advantage of its powerful FEA capabilities to find out how structurally sound our design really is. So I've got a couple of studies that I'd like to show. I've run them already, so we can take a look at the results, but more importantly the setup as well. So one of the great things about SOLIDWORKS Simulation is its ability to work with symmetrical design. So you can see with this shed here, it's symmetrical both longitudinally along the length of the shed, but also transfers if you had a cutting plane over here. So that means that when we go to SOLIDWORKS Simulation, we can accurately simulate and reduce our time by modeling or simulating just on half or even a quarter of the model. So how might we do that? Well, I've got a configuration here. If we take a look, I'll just activate that. And you can see what that does is it cuts out, and that's just a simple extrude cut I've applied there, cuts out 3/4 of the model, leaves us with a quarter. So when we then go to our FEA study, we need to take that into account. So we can do that with what's known as a symmetry fixture, and we can simply tell SOLIDWORKS Simulation that these are my faces for symmetry, or that lie in the plane of symmetry. Please take these into account when you solve the simulation. This first study, I've run everything in the model as solid mesh elements. This just helps with not having to worry about contact conditions or things like that. But in the other study, we'll take a look at how you can model as beams and save some time there as well. We then apply our forces. We've also fixed the base plates at the bottom, and then we can just simply take a look at our stress results. So even though we modeled only a quarter, or analyzed a quarter of the model, SOLIDWORKS Simulation still very helpfully allows us to view results across the entire model as if we had simulated. So you can see some obviously this is exaggerated. We can see some stress concentrations near where the connections are, as we would expect, and some bending. And one of the most interesting ways to analyze results in SOLIDWORKS Simulation is, of course, to animate it. So we can do that very simply. And animation is also what I would call a nice little sanity check as well. So a great way to see if your contact conditions, your fixtures, your loads are working as you expect them to. So once the animation is complete, it will play. So there we go. So we can see as the load is applied to these angled rafters here, we can see the loads being put on and the stress concentrations appearing, but we can make sure that our fixtures are working and our symmetry conditions are working as well. So the displacement and the stress is being felt symmetrically across both sides of the model. So that's a great way to check that our setup is correct. As for the stress, we can see the maximum stress is 8.3 megapascals approximately. And if we take a look at the material is a aluminium alloy in this case, and we've got the yield strength at 75.8 megapascals. So we're still well within our factor of safety ranges. And we can take a look at the displacement. and we get a maximum displacement of about 0.6 or 0.7 millimeters there as well. So one of the things is to see how long and how detailed the mesh was as well. I ran it with a fairly standard mesh, so we can see about 100 200,000 nodes and 600,000 total elements there. If we take a look at the solving time, so you can see it took about 50 seconds to solve in this case, which is not very much at all, particularly for a model, and a large part of that solving time is due to the fact we only analyzed a quarter. If we analyzed the whole model, it would take at least 4 times that amount of time. So this was, as I said, a simulation study just done with normal solid mesh elements, but because we're dealing with structural members here, and they are weldment features, so IC3D Steel automatically creates them as weldment features, it can be a good idea to use the beam elements in SOLIDWORKS as well. Of course, extra care needs to be taken with beam elements. So here in this particular study, I've analyzed the entire model. So I've sort of compromised between analyzing the entire model, but simplifying the solution time using beam elements rather than solid elements here. So you can sort of get away with that. Extra care does need to be taken when you're using a mixture of mesh elements such as beams and shells, or beams and solids, or shells and solids, while simulation does enforce as much as it can what's called as automatic bonding between the different mesh elements. It's always a good idea to manually force bonded contact sets between the different types of mesh elements as well. So you can see I've got a whole bunch of bonded contacts where my beams meet with my solid. So these plates, for example, can be treated as solid because their thickness is quite thick relative to their overall size, and so basically at all of these interfaces I've created bonded contacts to make sure that that doesn't stay together. So if we take a look at the mesh there, so we can just show the mesh. So there's a mixture of solid elements and our beam elements there as well. And we do have control with the beam elements if we want, in terms of applying mesh control. So you can apply mesh controls to improve the mesh quality in certain areas where you might be worried. So if we take a look at the results there, so when we have a mixture of mesh elements such as solids and shells, we have two distinct plots. So this is the solid plot for just the plates there. Not really much to look at. I'm just going to hide some of these simulation symbols to get them out of the way. But the more interesting plot is what's known as the axial and bending, or the worst case scenario for all of the beams there. So take a look at the axial and bending for the beams, and again we can animate that to see what's going on there as well. So again, you can see that our results are fairly symmetrical across the model. So we can conclude that our setup across both studies has been good. One of the good things with using beam elements is the diagrams that you can get, as well as the beam forces. So you can get both shear force and bending moment diagrams for all beams or selected beams as well. So if we take a look at bending moment, for example, and I just select a particular beam, it will go ahead and generate the bending moment, so you can see the exact point where the bending moment switches over, and use that for further calculations if need be. And if we go to solver messages, so we can find that took only 10 seconds even running the entire model, but simplified greatly because a majority is just simply the beam elements, which are much simpler than running the solid elements, much less amount of nodes there as well. So you can see that running with beam elements saves us a lot of time and gives us access to more results, or different results I should say, as well. And again, because this is a native SOLIDWORKS model, modeled in using IC3D Steel, any changes you make to the model, anything you add or delete, you can simply come back to the study, update it, run it again, and you'll have your updated results. So that's how you can use IC3D Steel in conjunction with SOLIDWORKS Simulation. Firstly, to create structural models quickly and efficiently with all of your connections, and then validate it in SOLIDWORKS Simulation to find out how structurally sound it is. So for now, thank you very much.